Okay, so it's Memorial Day. We don't have class, and yet we still have a homework assignment due. So, want to offer some extra support. Here's a topic that 3 students have attempted but unsuccessfully, called understanding the solvent leveling effect. There's actually something in here that I think is harder than it ought to be. I've already sent in a notice to ALEKS, and they'll fix it. But in the meantime, we've got to deal with it. So, chemist wants to perform a reaction showing this reagent. Okay. This reagent is sodium acetylide, pretty ugly, but since it's got a sodium on it, we know what it really is. It's an ion, right? It's acetylide. It's HC, triple bond C with a minus on it. That's what that is. And we're supposed to find out, can I use these solvents for it? Well, the real question is, and we did this with another video, is we talked about if I put these two things together. Let me rewrite this sodium acetylide the way your eyes see it. When you see this, you don't see that. What you see is this. C minus. And the reason you do is because it's got that sodium ion on it right there, okay? So you're asking yourself, all right, what's going on here is I've got this acid, or rather this is a base, and I'm putting it in with all these other things. Is it going to act like an acid? So I'm not sure I said that well. Let's write this out. Here, let's try the first one, okay? NH2 is it going to go in with acetylide, CH3 minus. And is it going to go into equilibrium with, is it going to take a proton off of there? NH minus plus acetylene, right? And we did this in a previous topic. The way we said that was, well, let's figure out what the pKa of this is. So you go look the pKa up of this, because that's the acid in this side of it, and here's the acid in the other side. You look the pKa's up, and you say, what are they? Well, this is called methylamine, and it looks like ammonia. So I'm going to take you back over to the website, okay? So here's our website, and we look over in the data tables. You see what I'm clicking over here? Look in the data tables, and we look for the pKa's. My fingers are not hitting it. pKa's right here for selected molecules. What the problem is, okay, so here's the mistake. The thing that ALEKS has done wrong. Let's get rid of that. Put this up here. All right, so we got to look for ammonia or amine, methylamine. Well, there's ammonia, which is 38, and methylamine is not on here. So we go, okay, well, methylamine probably acts like ammonia. So let's go back over here to the wrong page. Let's go back to the, okay, this is probably going to be about 38 because it looks like ammonia, right? But then we go to find acetylene on there. What's the pKa of the other acid? Where are we here? And acetylene's not on here. It needs to be. It ought to be. I can tell you what the pKa is, and if you look at the explanation is going to assume that you can figure out that the pKa is 25. It's not on the table. It ought to be. So what that means is the reaction is going to go in that direction, right? Because that means the stronger acid gets to act like an acid, so it's going to go that way. Well, it was already as acetylide in the beginning. That means it's going to be totally fine to put this in with methylamine. It's not going to go in this direction. It's not going to go that way because the pKa of methylamine is higher than the pKa of the conjugate acid of this base. That's what we're talking about, okay? So we go look up the pKa of this. This is 38. The pKa of this is 50, right? Because that looks like, watch this. Let's go back over there to the, let's go back over here to the, that hexane looks kind of like this ethane down here at the bottom, which is 50, right? So it's 50. Is benzene on here? Benzene's not even on here, but it's going to be a bad acid. Oh, there's benzene, C6H6. That's 43. And you can see that the fact that you don't have all these, this is 43. That of acetylene, the pKa of acetylene, the conjugate acid of this guy, is 25, right? So I said, oops. What's 43? No, that was benzene that was 43. Benzene's 43. Do we have anything on there that looks like an ether? We do have this. This was about 16. This is about 16, right? So you definitely can't do it with that because it's lower. That's going to act like an acid. And this diethyl ether, is that going to be in there? Let's go look. I don't see anything that looks like an ether. Nothing looks like an ether. Okay, so probably the closest thing, it's going to be in the 40s. It's going to be high. Because all you have is hydrogens bonded to carbons in diethyl ether. So that's going to be fine. This is not going to act like an acid. Wait, now I got to see the question. Check the boxes of those that are not supposed to be used. Okay, so that's fine. Methylamine is fine. Hexane is fine. This is not fine. And benzene is fine. Okay, so we're fine there. Let's do one more. And, right, so let's look here. Sodium bromide. Oh, I can tell you now. Everything's going to be fine because the conjugate... Let's go back over to our whiteboard here. Sodium bromide. We don't see sodium bromide. We see bromide, right? And the conjugate acid of bromide is HBr, which is a strong acid. So in other words, nothing's going to donate a proton to HBr, to bromide. We're never going to see this reaction go this way. Not going to happen, right? Because this is such a strong acid. So let's go back over here and say, this is, again, let's read the instructions. We should check the boxes of this. It should not be used. Benzene's going to be fine. The next one is diethyl ether. That's going to be fine. Dimethyl sulfoxide, you've never seen that before probably, but it's DMSO. But there's no hydrogens bonded to anything except carbons in this one. That's going to be fine. Isopropyl alcohol is going to be fine, right? Nothing's going to donate a proton to bromide. So we're going to say all these are acceptable, all of them. And let's do one more. Okay, let's do one more. Okay, so we're dealing... Oh, sodium bromide. We just did that one. Okay, let's do another one. Sodium... I don't even know what that's called. I don't even know. I should know what that is, but I don't. So it's sodium SH. Okay, so let's go back over to our whiteboard and say SH. It's minus, right? Because when we see the sodium, we see this right here. We know it's the sodium's off by itself. Okay, if it's a solvent, it's just the thiol maybe. I don't even know what that's. I should know what that is, but I don't. Sorry. So the question is this going to take a proton from anything? H2S. So what we're going to do is we're going to go look. This is the conjugate acid of that. Let's go look at the pKa table. The pKa table. Hopefully SH2 is going to be on here. And it is. It's 7. Okay, that's pretty low. It's 7. Let's look at these others. Okay, this is 7. Okay, let's go look at the other pKa's and see if there's anything lower than 7. If there is, then we're going to say, nope, can't do it with that. It's going to be too acidic. So methanol, we looked that up a minute ago. That's going to be fine. Methanol's fine because that's pKa is about 16. Diethyl ether, the second one down, is going to be fine. All it has is hydrogens bonded to carbons. It's going to be fine. Acetyl, there's a triple bond with a hydrogen at the end. That's going to be 25. That's not in your table. It should be 1, 2, 3, 4, 5. Okay, so it looks like that's a 5-membered alkyne, which we haven't learned a name yet. But it has a pKa of about 25. It's going to be fine. We're looking for something with pKa lower than this SH minus. Dimethyl sulfoxide, DMSO, is going to be fine because it's just hydrogens bonded to carbons. And water is about 14 or 15 or 16, so that's fine too. These are all fine. Check. I said one more. Let's do one more. This is our last one. Okay, take a look at this. Look at this isopropyl ONA. What is the, take a pencil, pause the video, take a pencil and write down the base that we're concerned about. Okay, we don't see that when we look at that. What we see is isopropoxide, right? And what's the conjugate acid of this? Isopropyl alcohol. So we can find an alcohol on there, and the alcohol in the pKa table is, get your eyes used to it. There's an alcohol at 10, but it's got the double bonds in there, which are conjugated, so it's probably not the one we're looking for. There it is, methanol at 16. Methanol at 16 is just the same as is going to be basically the same. Sorry for the background noise. My wife is here working with me, and she's doing hard work. So, okay, so this is going to be 16, right? And so consequently, if we see an acid on here that's lower, then it will probably donate the proton to isopropoxide. Let's go back over here. And the first one's hexane. No, that's got a high pKa. And then there's acetic acid. That's got a low pKa. That's unacceptable because that will donate a proton to isopropoxide. A diethyl ether again. That's got a high pKa, even though it's not on our table, but it only has carbons bonded to hydrogens. Benzene is on there. That's 43. That's not going to donate a proton. And ammonia is not going to donate. Okay? And that's it. So hopefully that's helpful. I haven't got questions from the class today, so I'm hoping, well, I got one, and I answered that this morning. Hopefully you guys are moving along. Let me know if you need more examples or help with this. Good luck.